LTSA-PCA is an extension to the LTSA tool that provides support for compositional reliability analysis using probabilistic component automata, a composable probabilistic model which clearly distinguishes between internal actions and the actions corresponding to interactions between components. This model also includes support for the representation of failure scenarios, failure propagation, and failure handling. In order to add support for PCA models in the LTSA tool, we propose a probabilistic extension to finite state processes on which LTSA relies for the specification of behavioral models. We will use an e-commerce system from the paper, A Formal Approach to Adaptive Software, Continuous Assurance of Non-Functional Requirements by Antonio Filieri and others, in order to demonstrate how LTSA-PCA can be used to construct probabilistic behavior representations of component-based systems. The e-commerce system consists of a web service that sells merchandising to clients and integrates three external web services: authentication, shipping, and payment. From the original discrete time Markov chain representation, we have derived a plausible architectural configuration and a behavior representation for each component. We will now show the probabilistic finite state process specification for the authentication service. An input action login user represents provided functionality from the authentication service to other components. After receiving a login request, the authentication service verifies the user credentials and then sends the outcome back to the component which sent the login request. According to the original DTMC model, this communication may fail with 3% probability. We can now compile the PFSP specification to a PCA model and draw its graphical representation. For instance, we can observe that all the transitions labeled with failure actions lead to the error state. We now consider the PFSP specifications for the remaining components, which have been previously defined, and then compose them in parallel to construct the overall system representation. Although the e-commerce component has two components bound to its provided interface, its PCA representation models a single-threaded component that can only serve one client at a time. As a result, we have to change its PFSP specification to take into account the system architecture. Firstly, the interface actions that represent interactions between the clients and the e-commerce service have to be relabeled in order to consider the interactions with the components. Secondly, since the new client and returning client PFSPs have actions in common, we have to add a prefix to their actions in order to distinguish them in the system model. The overall system representation can now be constructed. Due to the inclusion of internal behavior and use of send-reply messages to represent interactions between components, the composite PCA is bigger than the original DTMC representation. Nonetheless, the hiding operator can be applied to reduce the overall system model such that only actions denoting interactions between components are kept for the reduced representation. As a reduction algorithm preserves the reliability properties of the original composite representation, the reduced model is translated to Prism in order to analyze with less complexity the reliability properties of the e-commerce system. The reduced composite PCA can be translated to a DTMC model since it contains full probabilistic information about the system. We now consider a previously defined alternative representation for the e-commerce component and the client components for which failure handle behavior was added. In this case, when the authentication service fails, the e-commerce component handles the failure scenarios and notifies the clients. Both the client components and the e-commerce component stop their execution after this communication. As we can observe in the graphical representation, the failure scenarios for the authentication service are not represented in the composite representation, as they have been handled. According to the PFSP specification, these failure handling transitions lead to a final state. Furthermore, the existing behavioral analysis tools in LTSA have been extended in order to be applied to PCA representations. When analyzing the safety properties of the last representation for the e-commerce system, LTSA-PCA produces the shortest trace to a deadlock state. Safety analysis can also be used to verify the existence of failure scenarios that have not been handled. In summary, using probabilistic component automata to model the probabilistic behavior of a component results in a representation that is independent from the context in which the component is deployed. When considering alternative architectural configurations, the behavioral model of each configuration can be automatically constructed using the PCA representation of each component, as opposed to represent a complex system using a monolithical model. In addition, the reduction algorithm is used to mitigate the well-known problem of state explosion for composite models. As a result, it can significantly reduce the complexity of reliability analysis for component-based systems.